Okay, well, thank you very much to the organizers for inviting me to give this talk. I'm going to discuss so-called Ising model, what is actually very popular maybe in this audience because Ken Golden, first scientist who introduced this Ising model for CIs, and we worked with Yuping, Ma, and Ken to develop this model for meltpond. But today I'm not going to just repeat everything like many years we explaining what is the Ising model. I want to discuss new features of this model and new kind of application. And I want to build this talk from the different angle. Just a general introduction concerning climate modeling. Now we have many exciting projects. For example, ESA offering a new project Digital Twin Earth, when we be able to emulate processes in the climate system like in real time and reproduce and predict different scenarios of developing of the climate system. And this is not a really novel idea, but the methods what actually we need to use maybe to revise. And the idea of the all global climate models and Earth system models, we build this model based on climate emulators. And there is no specific really rigorous term what is a climate emulator, but IPCC defining climate emulator like a reduced physical deterministic model what can help to build bigger model. What is not actually true, because we have many different kind of emulators, not only physics-based emulators, we have statistics-based emulators, just data analysis and some statistical modeling, and then it will be a statistics-based climate emulator. So the idea is, if we want to improve our climate modeling and build the new like a digital twin of our planet, based on the artificial intelligence, basically machine learning, maybe we need to change approach to climate emulators. And one of these ideas, what we just recently published, how to revise maybe this approach, instead of using physics-based model and statistical-based models, we can combine it and make a stochastic-based model. And after that, it's supposed to be data-driven models. And after that, if we have such low-dimensional reduced stochastic models, we can fit Earth system models and emulate the processes. And machine learning, it will be part of the simulation, what will help us to work with big data. And if we study CIs, because we'll concentrate on CIs, we need to build such stochastic models, data-driven models, and we want to build it on some nice physics, plus we want to make some discoveries. And how to, because we need to understand some critical processes in CIs, and when we need such a model. And as well as it will be good if such a model can provide a new mathematics. And the Ising model, what we introduced actually, it's a great example of such climate emulator, CI simulator, what combining both things, new physics and new mathematics. And hopefully it will be useful to fit Earth system models to make better emulation. And just want to remind what's going on, how we find this, what we need to use Ising model to reproduce meltponds on the Arctic sea ice. Again, this we can discuss yesterday, like from the image analysis, we observed fractal dimension transition, and fractal dimension here I want to just emphasize it's like a geometrical parameter, nothing else. If you want to discuss geometry, describe geometry of patterns, we can use this simple parameter, what actually connection between area perimeter, and that's it. But easy to derive. And also, when another thing, it's a critical transition in fractal dimension. And the second thing, if you look at the MeltPond's picture and the magnetic domain picture, we see some similar patterns, but the scale is absolutely different. And the idea came from statistical physics. If we can describe magnetic domains using statistical physics model, let's try to describe MeltPond. And also everything it's related to more global problems, like and all this work what I will show it just in the frames of the NSF project about modeling, statistical physics modeling of algae bloom beneath sea ice. And so this is the point. This is like a motivation from sea ice and how to build such emulator. And this is the motivation from data science. We found this similarity that some statistical physics models can be good to describe the meltwater. But an Ising model, what we got based just on physics, actually it's machine learning model called the reduced Boltzmann machine, what actually providing unsupervised learning. And it's actually amazing because it was introduced early, much early when anything like machine learning appeared, such Boltzmann machine, and many other models in statistical physics like Maxwell's demon and so on. But it can be used, and people using it in machine learning. In terms of statistics, this Ising model, it's a Markov networks, and another feature can be discovered based on this knowledge. But what the idea of just a Boltzmann machine and the special case of this machine, it's a Ising model. We have two layers in this machine, like a real layer and a hidden layer. And there is some interaction between these layers. And the nodes are supposed to be random variables. And actually, they can be parameterized through the weights of the connection. And these weights can be related to the energy function. So all interaction is supposed to be described through the energy function. What is again describing through some kind of probability of processes happening in this Boltzmann machine. And another thing, it's this machine is restricted, and because you can put some condition on interaction between these layers. And it's a basic idea when you can make some kind of unsupervised learning, if you're able to derive this energy function and the connection between these nodes, you can the machine can learn from this energy function how to build dynamics. And by the way, I didn't show, but I saw how we reconstructed images from actually noise using the Boltzmann machine. But by the way, people may not really like it because it's really like a time-consuming process. We have more and better methods maybe. But historically anyway, the Boltzmann machine is a Ising model. What in terms of physics, what is the Ising model? If you have a magnet, we can in two-dimensional magnet, we can represent these magnetic domains through the interaction of the spins in this lattice, and some spins are lining up, some spins are lining down, and the configuration of spins goes through this probability, what is gained as a function of energy. And we building this energy based on the interaction between these spins and some external influence on these spins. So it's again the same idea like in this Boltzmann machine. But physics is more beautiful because you can observe critical transition in this model from ferromagnet, if it's a magnet, to anti-ferromagnet, from order to disorder, driven by some critical temperature in the system. And this model can be connected to the differential equation. If you have a magnetization, the number of spin, for example, align up or down, it's a first derivative of the free energy with respect to magnetic field, and we have a critical transition at this point. If you have magnetization, you can describe this critical transition. It's not a model for magnetics only. This model it was used in climate science, for example, to describe the convection, tropical convection, or in ecology to describe pistachios trees synchronization and blooming. So very popular model. Let's just briefly discuss how we can apply this model to meltponds. Again, the same idea, they need to build the energy, the Hamiltonian, how the ponds are interacting, and some kind of external, what is external magnetic field, what influence on that interaction. And supposing spin, positive spin, it will be meltwater, and negative will be ice, and the magnetization, it's supposed to, and the order parameter in our case, it's supposed to be the fraction of up spins, so the pond fraction. And the spins are interacting, neighboring spins are interacting, and neighboring ponds, as well as some external field influence on that interaction. And this we found that this external field is supposed to be pre-melt ice topography. And pre-melt ice topography is a random variable, like something like this. And it's actually a driver of the spin interaction in such a system. And what we need to know, it's just a single physical parameter, what we need to know to run this model. Just for simplicity, we assume like this random field is just independent Gaussian, nothing else. Plus, we need to ensure that we have some good physics in that model. And first, if we're modeling two-dimensional processes, we need to know the lattice size. And from data analysis, we found the lattice constant, it's supposed to be 1 meter. And after that, another thing, we introduced the tire breaker rule, how the neighboring spins interacting depends what we have. We have ponds around or ice around. And you can consider this like a parametrization of this model coming from observation, but not only. It's also coming from the theory. And actually what we had, we can make Monte Carlo simulation in that model. And the main positive thing with this model reproduces the fractal dimension transition, but the critical may be the onset of complexity at 90 meters squared. But yeah, but observation 100 meters squared, and the scaling exponent also pretty close. Again, some real data and observational comparison between real and observations and this model. And so this model is just a validation, and this model, we can say it can work well, reproducing this transition in fractal dimension. So what we can do, what the next step? The next step, before considering how to use this model in emulators, let's discuss a new map what actually arising from this model. The star breaker rule what introduced how the neighboring spins are interacting. It's coming from some simple physical assumption, but as well as coming from in physics, it's called Glauber single spin flip dynamics. The idea why we need to use this kind of spin flip dynamics coming because we use a random field, and it's kind of not a classical model, it's a random field Ising model, plus the temperature, because in the classical model the temperature is one of the key parameters, the critical Curie temperature, but in that model temperature close to zero, and temperature cannot be a driver of critical processes in that system. And for such system, we may introduce the random field. We can use this Glauber single spin flip dynamics. What is actually, if the discussing in terms of Hamiltonian, it shows some rule. If we have energy lowering or energy rising, and on energy neutral or conserving processes, how this spin should interact. This kind of simple rules, and it's coming from the ideas of metastability in such system, because random field Ising model can model processes of metastability, and MeltPondNet we found it's like a metastable status in such system. And the general spin flip rate, actually in this system it will be like the function of this spin interaction, and anyway the critical temperature, it's inverse critical temperature. So the temperature anyway just implicitly appearing in this model. And when we look at this model, the understanding, like if we have ponds covering sea ice, during this interaction there is a heat exchange between ponds. They're interacting, and when increasing the thermal processes, heating, and more ponds appearing. But we remember the magnetization in this model is a pond coverage. So if we have more and more ponds on the surface, we increase in this magnetization. So there is like a coupling between magnetization in this model, pond coverage, and the interaction, increasing pond coverage. And when it's a kind of new model, we call it feedback Ising model. And feedback, generally, it's a general Hamiltonian for such model. This model, we extended it to the model on the complete graph. And general features of this model, that we have a coupling positive constant. The coupling constant is a positive for all magnetization, what is greater than -1, and it's a so-called representation of more ferromagnetic interaction in this model, because ferromagnet, when spins are lining up, it's a ferromagnet or in our case it's like MeltPondNet. And here are some features of this, new features of this model, the definition of this model. But the exciting thing, if it's just a Hamiltonian, but if you look at the mean field theory and find the magnetization in that case, the thing is, as I said, the magnetization is the first derivatives of free energy. And when deriving these equation for magnetization in such model, we will get such transcendental equation for magnetization in the feedback Ising model. And if you want to get the phases, ordered, disordered phases coming from this model, a critical temperature. So I will show just a nice picture of what we got. So if this is the plot feedback Ising model. We plot for magnetization versus inverse temperature. And this is the classical model. Here, magnetization inverse temperature, not just temperature. So in the classical Ising model, we see the ordered phase goes to disordered phase and again to ordered ferromagnet, disordered phase, and anti-ferromagnet. Doesn't matter, it will be inverse temperature or just temperature. In our model, we have, let's say, like two magnetizations, M plus and M minus. What actually doesn't look like a smooth process here. It's a little bit different. Some in terms of dynamical theory, the bifurcation appearing at some range of critical temperature. Because in classical Ising model, we have just one single number for critical temperature called the Curie temperature, and any material has assigned Curie temperature. Here we have actually two critical temperature in this feedback model, approximately 0.7 and 1. And then here we have slightly different transition from disorder to order. And we have actually, and it depends on what is the critical temperature in this model. What is the critical temperature? So, and then again, we can, in terms of stability and instability, we can see that for intermediate, some kind of, if we have high temperature, low temperature, but for the intermediate temperature here, we have actually bistable phase and plus. And by stability in this such system, it's some kind of new feature, what actually send us to hysteresis in such a system. So hysteresis, it's phenomena in magnetics what's supposed to be observed. I took from some textbook the explanation of hysteresis for the classical magnets. But for the feedback Ising model compared to classical Ising model, the hysteresis appearing too. In classical Ising model, the hysteresis is not coming from that model. But if you have feedback Ising model with oscillation, some kind of this simple oscillation, we can observe hysteresis in that model. What is again some kind of positive good feature. And if we apply it to MeltPonds, go from these general features of this model, go back to MeltPonds, assuming what I said, if we have a ice-albedo feedback, more ponds, pond fraction increasing, magnetization increasing, and this coupling actually works well. We see the pond coverage versus the effective external magnetic field, what is the interaction between spins plus this external field, what in our case actually how water level in that system is changing. We see again some interesting feature. If the MeltPond coverage, if you take the first derivative of MeltPond coverage, we have the second order phase transition in this system. And this second order, it corresponds to the clusterization of ponds at some certain time, what we actually observe in real life. And these ideas can be applied, what we working with Pavel Krapivsky now, to social system. When people congregating, they have some beliefs and they like really isolated, but at some certain, if they have some feedback, they can also congregate and organize protests, churches, and so on. So this is that idea. And another thing, yeah, I have another thing to develop to ensure that model will work well. We need some. We develop some new machine learning architecture for image analysis of complex boundaries of meltponds, because what initially can found from these images, we want to extend it and double check this complexity. And this architecture for image analysis of meltponds, we call it MeltPondNet. It's based on UNet networks and has some nice feature. And even we can get 4 classes in this model: pond, snow, open water, and submerged ice. So we can detect all these 4 classes, and compared to other machine learning method, it works well. Why they need it? It's the last thing what I need to say. So when, as I said, the main problem in this Ising model, we need to get pre-melt ice topography. What we assume it's like it's a random field, and we use a Gaussian to reproduce it. But instead of it, if we have a real images, we can employ so-called generative adversary networks, GANs. And to this feature of these networks, it can not only analyze images, real images, and we can get real data from that images, but also it can produce fake patterns, fake or synthetic patterns based on the feature of that data what we provided. And this, why we need it? Because we can get many different configuration of pre-melt ice topography. If we have the real data and it goes through GAN, and when we can run this Ising model like real emulator, and we can see many different scenarios based on our real data. So the main conclusion is the highly theoretical 100 years old Ising model, what we just used initially to reproduce meltpond patterns. It gives us nice, great new mathematics, interesting physics of sea ice, and plus new application in terms of climate emulations. Thank you.
Thank you, Ivan. So we got time for a couple of questions.
Hi, Ivan. Sorry, well, I suppose I have a comment and a question, I suppose. I'll start with my actual question, which is, you might not have studied this. You showed in the Monte Carlo simulations the transition in the fractal dimension, or the onset of complexity, at a pond size of around 90 meters squared, I think you said. Okay, and 90, yeah. So I guess my question really is, how sensitive is that to the underlying topography? Because I understood that you assumed a Gaussian distribution with topography. I mean, the actual isotopography likely isn't Gaussian, but okay. If you were to change the standard deviation or the properties of the Gaussian distribution, does that have an impact on the transition to complexity?
Yeah, thank you for my question. So yeah, we didn't study it, but yeah, the idea is to continue this research to get maybe not even, we wouldn't operate with the Gaussian and even noise or any additional things, right? But instead of that, to use real data. What we didn't, it's not done yet. Yeah.
So it likely is sensitive to it, but you haven't explored that yet.
Yeah, we'll see. I cannot say what we will get. We'll get the same yeah, same curve or not. Yeah, it's a good question.
Next one. Yeah, I'm not sure I really understood the full details of the feedback Ising model, but or Ising model. But it seemed to me that they had long range connections between different spins or different elements. Okay, and I wondered how that connected with what Ken was talking about yesterday in terms of the critical points being the saddle points in the topography. It's not clear to me that a melt pond in location A is in any way physically connected to a melt pond in location B, which is some distance away, because of the catchment areas of the meltwater. So it wasn't clear to me that that aspect of the Ising model translated very well to the physical simulation of melt ponds.
Yeah, correct. It just this. You mean some kind of interaction between spins, and the actual we cannot incorporate and even wouldn't incorporate detailed physics, the heat transfer, what's going on. But in terms of this model, feedback model, we're just making simple assumption, increasing making more spins aligning up, we increasing magnetization, what is a pond fraction. And this is a coupling. More ponds, magnetization is increasing, and you get ferromagnets actually in terms of. But the idea of this model to incorporate just a single parameter and avoid any other physics. And maybe you're right. If we closely look at the heat transfer in the system, yeah, we can get some other features. Yeah.
Okay, thank you.
Thanks, Ivan. So we're going to need to move on to our final speaker now. So finally, we've got Agnieszka Herman.